Okay, looking at this picture, somebody chose, maybe I flipped a coin, I don't remember. This vector we take to be the F vector, this vector we take to be the delta S vector. Okay, the first thing we do is we project F on delta S. We get this projection, so we take, we sketch a rectangle. One side representing the magnitude of this projection, and of course that would be F cosine theta, wouldn't it? Okay, and this side representing the magnitude of the delta S vector. Okay, we sketch that, we shade it in, and we say that, well, clearly these two are in the same direction, so we have positive work. So that the area of this, the positive of this area represents the work done by this force moving through this displacement. Now, also in a different color, I projected delta S onto F, and I got this projection. Okay, now this projection represents what? Delta S cosine theta. Right here's your right angle, here's your hypotenuse, here's your adjacent side, side adjacent to theta. So this has got to be delta S cosine theta. Well, I take a vector, or a side, whose length is equal to the magnitude of this vector, and I put it down here. Now I didn't have room to write it as big as I should have, but this side represents delta S cosine theta, this projection. This side represents what? Just the whole vector F, the vector on which we projected the other. Okay, so this rectangle has dimensions F by delta S cosine theta. This rectangle has dimensions F cosine theta times delta S. I've got a positive in both of them because in either case the projection is in the same direction as the vector we projected on. Well, clearly if I multiply this by this, I get the same thing as if I multiply this by this. These two will have equal areas if they're constructed. If you carefully construct this with compass and straight edge and do it with complete accuracy, you're going to get two rectangles with identical areas, even though their dimensions, relative dimensions, are likely to be different. Because there's no reason to expect that the width of this rectangle is the same as the width of this rectangle. Okay, the width of this rectangle is your whole force. The width of this rectangle is your whole force times cosine of theta, which is close to the same size. And actually, if I did this accurately, this side would be shorter than this because cosine theta is less than 1. Okay, well, you need to sort all that out. Draw your own set of vectors. Get a compass and straight edge and construct this thing and see what you gain from doing that. You don't have time to do that, and I know you won't, but if you do have time, you ought to. Really convince yourself of the meaning of the dot product and how it can be represented as a vector. That allows you to look at a force and a displacement vector and visualize, let's say that allows you to look at a set of force and displacement vectors and visualize how the work compares. Okay, if the force and displacement scales are the same on all of these, where is the greatest work done? Well, pretty clear that this is the biggest rectangle. This is probably the one with the least area. This rectangle has the greatest area, or either of these has an area greater than this one. This one's just too thin. But it's not so thin that its excess length doesn't compensate for this one, I don't think. So I'm thinking the area of this one is less than the area of this one, is less than the area of this one. So if I have these forces and displacements, and these forces and displacements would ordinarily be considered in the context of some real problem, you would have a visual representation that you can fairly easily use to determine where the greater work is being done, where positive work is being done, where negative work is being done. So I think it's a useful connection.